In this section, we're going to introduce inner product spaces where we'll take the main properties of the dot product and generalize them to what's called the inner product. So in doing so, we're going to bring the geometric concepts of length and angle to more general vector spaces. And even if we look at the vector space Rn, if we change the inner product to something different than the dot product, you can alter the usual geometry of a vector space. Okay, so as we said, the inner product plays the role of generalizing the dot product to arbitrary vector spaces. So the inner product, which we use this bracket notation here, the angle brackets. So like the dot product, the result of the inner product is a real number and not a vector. So the result of calculating the inner product say UV is a real number and not a vector. Okay, so like we did for abstract vector spaces, to define the inner product, essentially you take the four defining properties of the dot product and use them as the definition for the inner product. So basically, if you can define an inner product that satisfies these four properties, then you can carry over the functionality of the dot product to an arbitrary vector space. And so anything that satisfies these four properties will carry over the other properties of the dot product, right? So we can define the length of a vector as the square root of the inner product of the vector by itself. The distance is defined in the similar way. Angle, again, is defined in the similar way, with the inner product replacing the dot product. And two vectors are orthogonal or perpendicular if their inner product is 0. And we also have the Cauchy-Schwarz inequality. So, as we can see, the inner product will carry everything that we know about the dot product to more general vector spaces. So here we look at an example of an inner product on the vector space of 2 by 2 matrices. So to define the inner product, we have to show how to calculate using the coordinates of two arbitrary matrices. And it's defined in this way. Right, so you have two matrices A and B, and the entries playing the role of the coordinates of the matrices is defined as 2 times A1, 1 times B11 plus A21 times B21 plus A12 times B12 plus 2 times A22 times B22. So one thing to notice about this inner product is, you can see that it's commutative, right? Because if you switch the roles of A and B, the sum is still the same. The result of this is a number, and if you take the inner product of a matrix, a 2 by 2 matrix by itself, then this quantity is the first entry squared. This is the square of this entry. This will be the square of this entry, and this will be the square of this entry. And so it's again a sum of squares, and so it's always going to be non-negative. But one thing to be careful about this inner product is when we calculate things like length, distance, and angle, even if you think of a matrix as a four-dimensional vector, right? Because essentially it's just something with four real number coordinates. You shouldn't think about visualizing the geometry in the same way as the standard inner product, because the standard inner product doesn't have the coefficients of the terms for the dot product is all 1, whereas this has a coefficient 2 for this term and a coefficient 2 for this term. So these coefficients are called weights, and by changing the coefficients in this way, you can change the geometry of the vector space. And so when you think of something like a 30-degree angle, it's not the same as the normal way you think of a 30-degree angle. Okay, so in any case, here we're going to calculate the various things for these two particular matrices, A and B. So to calculate, we just apply the formula for the inner product, right? So this entry is A11, A12, A21, A22, B11, B12, B21, B22. So the inner product of A with B, so it's 2 times the product of the first entries here, so 1 times 0, then A21, B21, so that's this entry here, right? So 2 times -2 plus then -1 times 1, and then plus 4 times 2, the weight 2, times 4 times 0. So now we calculate, so this is 0 minus 4 minus 1 plus 0, which is equal to -5. Okay, so that's the inner product of A with B. Right, so again, we're just applying the formula for the inner product in this case. And now we calculate the length of A. Right, so the formula for the length of the vector is the square root of the inner product with itself. So first we have to calculate the inner product of a vector with itself, right? So let's do that. So again, the weight 2, and then this entry times itself, plus this entry times itself, so 2 times 2, plus this entry times itself, plus 2 times this entry times itself. Okay, so what do we get? So we get 2 plus 4 plus 1 plus 32, and this calculates to 39. Okay, so now we can just take the square root of this, which is the square root of 39. Okay, so now to calculate the length of b, this is similar, right? So we take the inner product of b with itself, 2 times this entry squared plus this entry squared plus this entry squared plus 2 times this entry squared. Okay, so what do we get? This is 0 plus 4 plus 1 plus 0, so that's equal to 5. And so this is the square root of this number. So we get the square root of 5. Okay. So now we're asked to calculate the distance between the two matrices. So what is the distance between two matrices? It's the length of A minus B, thought of these two matrices as thought of as vectors. All right, so we first calculate A minus B. So what do you get? 1 minus 1, 2, 4, minus 0, 1 minus 2, 0. And the result is 1 minus 2. 2 minus a negative 2 is 4. 4 minus 0 is 4. And then now we have to take the inner product of this with itself. So 2 times this entry squared plus this entry squared plus this entry squared plus 2 times this entry squared. So this is 2 plus 16 plus 4 plus 32, which gives us, so that this is 48, this is 50, 54. Okay, and then finally the distance from A to B is given as the length of A minus B, which is calculated as the square root of the inner product of A minus B with itself, and which we calculated as the square root of 54. Okay, so as I mentioned before, even if you think of a 2 by 2 matrix as a 4-dimensional vector, because the formula deviates from the ordinary dot product by these coefficients of 2 for these two terms, you shouldn't think of this distance as calculating the straight line distance between these two vectors. Because the geometry has changed because of these two coefficients. Okay, so so similarly, when we calculate the angle, you shouldn't think of this as the ordinary angle as you typically think of. Okay, so now we calculate the angle, so we use the formula. So cosine theta is the inner product of A with B divided by the length of A, length of B. Right, so all of these things we've calculated previously, right? So the inner product of A and B was -5. Length of A was square root of 39. Length of B was square root of 5. So to calculate the angle, we just take the inverse cosine. -5, and then square root of 39 times square root of 5 is square root of 195. So calculating this, so I want inverse cosine. So first, make sure it's in degree mode if I want the answer in degrees. So cosine inverse -5 divided by square root of 195. So I get about 110.98 degrees. In this example, we'll look at an inner product defined for a function space. So the vector space C bracket A comma B is the vector space of continuous functions on the closed interval AB. So if you remember, this vector space of functions is infinite dimensional. And so when we define the inner product, we have to be a little bit careful, right? Because the inner product of two vectors, when you calculate it, should be a finite real number. Okay, so for two continuous functions f and g, we'll define the inner product of f with g as the integral over the closed interval a, b of f of x times g of x. So if we look at how the inner product is defined here, you can sort of think of it as being analogous to the dot product, right? Because what is the dot product? It's just the sum of the products of the coordinates of the two vectors, right? So in this instance, my two functions f and g, you can kind of think of the coordinates of the functions as being the function values at each of the points on the interval, right? So f of x is the coordinate at the point x, and g of x is the coordinate at the point x. Okay, so you can think of this as being the product of the corresponding coordinates, and then now the integral is playing the role of summation. But one thing to notice about this is because f and g are continuous on a closed and bounded interval, this integral is guaranteed to be a finite number, and so the inner product is well defined. So so that's why we take the vector space of continuous functions. If you have a function that's discontinuous, where it goes to infinity somewhere, and then you have an improper integral where the integral is infinite, then this would not be well defined. But here we restrict to continuous functions, and so everything is okay. Okay, so basically the four properties for an inner product follow from the properties of integration. Right, so if you switch f and g, it's still the same, and then the integral is linear. So so the other properties follow. Okay, so let's look at an example where we calculate the inner product of two continuous functions. Right, so the two functions we're going to look at is f of x is going to be the function x, and g of x is the exponential function e to the 2x. So both of these functions are continuous everywhere. So they belong to, and then we're going to specifically look at the interval from 0 to 1. Okay, so a is 0 and b is 1. Right, so if I want the inner product of f with g, following the formula here, this would be the integral from 0 to 1 of f times g. So that will be x times e to the 2x. So here, because I have the product x times an exponential, to calculate this integral, I can use integration by parts. So if you remember, the formula is uv, and because we have a definite integral, where the integral is from 0 to 1, you have to evaluate from 0 to 1. So minus the integral from 0 to 1 v du. Okay, so this will be my u, this will be my v. So u is x, dv is e to the 2x dx. Now I need to calculate du for this part. So derivative of x is just 1. And then now I need to calculate v. So I integrate this, right? So you integrate dv to get v. So integrate this integral of e to the 2x is 1/2 e to the 2x. Okay, so now we can calculate this integral, right? So u times v is this times this. So we get 1/2 x e to the 2x. Evaluated from 0 to 1 minus the integral from 0 to 1 of v times du. This is v, this is du. So the product is 1/2 e to the 2x dx. Okay, so evaluating over this interval means you plug in the top number for x, and then minus, and then plug in the bottom number for x. Okay, so if I plug in 1 for x, I get 1/2, this is 1, and then the exponent here is going to be 2, so 1/2 e squared, and then then I subtract, I plug in 0, this x becomes 0, so the whole thing will be 0. Okay, so that's this part, and then now minus. So to calculate this integral, I need the antiderivative. So the antiderivative of this, so again the 2 comes out, so in the denominator, so 2 times 2 is going to be 4. And then antiderivative e to the 2x gives me e to the 2x, evaluated from 0 to 1. Okay, so this part is done, so that stays the same. So that's just 1/2 e squared, and then minus. I need to plug in 1, so this becomes 1/4 e squared. Then I plug in 0, so minus. Plug in 0, this is e to the 0. But then e to the 0 is just 1. Right, so I get 1/2 e squared minus 1/4 e squared. Then minus minus becomes a plus. And then e to the 0 is 1, so this is 1/4. And then these are like terms, so 1/2 minus 1/4 is 1/4. So we get 1/4, and then I can factor out the 1/4, so I'm left with e squared plus 1. Okay, so e squared is a number, so that's e squared plus 1, and that's a number, and then times 1/4, that's a number, right? So this whole thing is just a real number, and so that's the inner product of f with g. Okay, so so let's continue on, right? Because this is a valid inner product, so we have the concept of length, right? So we can think of trying to calculate the length of a function. But one thing to be careful about is that this notion of length is different from arc length, which you might have learned in calculus. Okay, so you should just think of this length as something coming from the inner product and not related to anything about the length of the graph or anything like that. Okay, so the length of the function is the square root of the inner product of a function with itself, right? So so first we have to take the inner product of f with itself, and so again, the formula for the inner product is from integration, right? So this is the integral from 0 to 1, x times x, because f of x is the function x. So x times x is just x squared. And so the antiderivative of x squared is x cubed over 3. Need to evaluate from 0 to 1. So plugging in 1, you get 1/3. Plugging in 0, you get 0. So this is 1/3. Oops. So the inner product of f with itself is 1/3. And so now I need to take the square root of this to get the length. So it's just 1 over the square root of 3. Okay, so again, you shouldn't think of this as being the same as arc length or anything. Any relation of this number to whatever the arc length of this graph is only a coincidence. Okay, so now let's calculate the length of g. So again, it's the square root of the inner product with itself. Right, so first I need to take the inner product of g with itself. So I have to calculate the integral from 0 to 1. What is g of x? G of x was e to the 2x. Right, so e to the 2x times e to the 2x. So multiplying two exponentials, same thing as adding the exponents. Right, so this is the integral from 0 to 1 of e to the 4x dx. And then now we need the antiderivative. So the 4 comes out as 1/4. And then e to the 4x stays the same, evaluated from 0 to 1. Okay, so now plugging the numbers in. So what is this? So when x is 1, you get e to the 4th, and so minus, and then when x is 0, this is e to the 0. But then e to the 0 is just 1, right? So I can factor out the 1/4, e to the 4th minus 1. Okay, so that's the inner product of g with itself, and then as before, take the square root of this inner product to get the length. So I take the square root of 1/4 e to the 4th minus 1, and square root of 1/4 is just 1/2. Right, so I can write it as 1/2 square root of e to the 4th minus 1. Okay, so this is the length of g. Again, not to be confused with arc length. On this page, we discuss what's called the orthogonal projection of a vector u onto a vector v. So orthogonal projection is useful in physics where you have some vector quantity acting on an object, let's say in motion, and the only contribution of this vector comes from the portion that is parallel to the direction of travel. Right, so like, so for example, say you have an object in motion, and then you push it in some direction. If you, right, so like say you have a box, and you apply a force to it, and if the application of the force is in the same direction as the direction of travel, then all of the force is contributed to the motion. But again, if you have an object in motion, but then the force is is not parallel to the direction of travel, then only some of the force contributes to the motion. Okay, so this is the situation where we want to discuss, right? So we have two vectors u and v. Right, so we say v is pointing in this direction, u is pointing in this direction, and what we're going to call the projection of u onto v is, if you imagine forming a perpendicular between the two vectors, so form this right triangle, then this portion of the right triangle that's pointing in the same direction as v, so this is what we call the projection of u onto v. Right, so imagine like you have the sun, and then the sun casts a shadow for the vector u onto v. This shadow is called the vector projection. Okay, so because the two things are parallel, so projection of u onto v is parallel to v because they point in the same direction. We get that projection of u onto v has to be some scalar multiple of v. And then also, because you have a right triangle here, if I look at the angle theta, cosine theta for a right triangle is the adjacent side over the hypotenuse. So the adjacent side is given by the projection. And the hypotenuse is given by u. Right, and then we know that projection is just a multiple of v, right? So this is a multiple of v over the length of u. So the reason I take a here and not the absolute value of a is, so a could be positive or negative, right? And so this could be positive or negative, and the reason I'm leaving it like this, being positive or negative, is because in the diagram I've taken u and v to form an acute angle, but it's possible they could form an obtuse angle like this, right? So when it's acute, a is positive; when it's obtuse, a is negative, and that's taken into account with the angle, right? So that's why I leave a without the absolute value, because it could be positive or negative. Okay, so we have cosine theta is equal to this, but because u and v are vectors, we can also calculate the angle using the cosine formula for vectors. Right, so the angle between vector u and vector v is given by cosine theta is equal to u dot v over the length of u, length of v. And so we have two expressions for cosine, right? So I can set them equal to each other. Right, so So what do we have? A times v over u equals u dot v over the length of u, length of v. Right, so the length of v is both in the denominator, right? So they cancel out. And sorry, that's the length of u. Right, the length of u. So that cancels with this. And so if I solve for a, I can divide this over, right? So a is equal to u dot v over the length of v squared. The square of the length is just the dot product with itself. Right, so this becomes let me instead of writing as the dot product, let me write as the inner product to be more general to any vector space. So this is inner product of u with v, inner product of u with v, inner product of u with v, and then again the square of the length is the inner product of a vector with itself. Okay, so the projection of u onto v, right? So this is a, right? So it's just this times the vector v. Right, so when you calculate this projection, this whole quantity is just a single number, and this quantity is a vector, right? So it's a number times a vector, and so the result should be a vector. Okay, so this is the formula that we have for the orthogonal projection. Okay, so in this example here, we're asked to calculate, using the standard dot product, to calculate the orthogonal projection of this vector u onto v, right? So we just apply this formula. So the inner product is just the dot product, right? So u dot v is equal to 6 times 1 plus 2 times 2 plus 4 times 0. So this is 6 plus 4 plus 0, which is 10. And v dot v is, so this vector dot with itself, right? So that's 1 squared plus 2 squared plus 0 squared, which is equal to 5. And then now we can put it together. So the numerator here is 10. The denominator is 5. And then the vector v is this vector, so 1, comma 2, comma 0. So 10 over 5 is 2. So 2 times 1 is 2, 2 times 2 is 4. So this is what we get as the vector projection. Okay, so in this last example, we're going back to the vector space of continuous functions on the interval 0, 1. And we're asked to calculate the projection of f onto g for the two functions f of x and g of x that we looked at in the previous example. In this example here. Okay, so the projection of f onto g the formula is just the inner product of the two things over the inner product of G with itself times G. Right, so because we need these two inner products, luckily we've already calculated it in example 2. So what was the inner product of F with G? This was calculated as 1/4 times E squared plus 1. And then the inner product of G with itself, we've also already calculated it. So inner product of G with itself was 1/4 e to the 4th minus 1. Okay, so now we can just plug everything in, right? So this is 1/4 e squared plus 1 over 1/4 e to the 4th minus 1. And then the function G was e to the 2x. So if you notice, e to the 4th minus 1, this is a difference of squares, right? So it's just e squared minus 1, right? So factoring the difference of squares, you get e squared plus 1 times e squared minus 1. And this e squared plus 1 cancels with this one. 1/4 cancels with this one. So what are you left with? Right, so this e to the 2x goes into the numerator. And then the denominator, this has canceled out. And this becomes e squared minus 1. Okay, so this is what we get as the projection of F onto G. Right, so e to the 2x is a function we think of as a vector, right? And then this is 1 over e squared minus 1 is the coefficient, right? So it's just, so we can see that it's parallel to this vector.